Chapter 1, Exercise 11. Hints. Use properties of an absolute value of a complex number from Theorem 133. Solution. Consider the case z equals 0. Take r equals 0 and w to be any complex number with absolute value w equals 1. Then, z equals 0 equals rw. The needed representation exists, but is not unique. Consider the case z not equal to 0. Let r equal absolute value z greater than 0, and w equals z over r. We note that absolute value w equals absolute value z over r equals r over r equals 1, and z equals rw. On the other hand, if z does not equal 0, and z equals rw with r greater than or equal to 0, and absolute value w equals 1, then absolute value z equals r absolute value w equals r. It follows that w equals z divided by absolute value z. The needed representation exists and is unique. Comments. Consider a non-zero complex number z equals x plus yi, and write it in the form z equals rw, where r equals absolute value z and absolute value w equals 1. We have w equals u plus vi with u squared plus v squared equals 1. So there exists theta in R such that u equals cosine theta, v equals sine theta. The representation z equals absolute value z times cosine theta plus I sine theta is called the polar form of z. The value of theta, an angle, is not defined uniquely. It is defined up to the summand that is proportional to 2 pi. Polar form of a complex number z equals x plus iy. Consider complex numbers in polar forms. Z equals absolute value z times cosine theta plus I sine theta. V equals absolute value v times cosine phi plus I sine phi. Then, zv equals absolute value z absolute value v times cosine theta plus I sine theta times cosine phi plus I sine phi equals absolute value z absolute value v times cosine theta cosine phi minus sine theta sine phi plus I cosine theta sine phi plus sine theta cosine phi equals absolute value z absolute value v times cosine theta plus phi plus I sine theta plus phi. Thus, the geometry of multiplying complex numbers reduces to multiplying the absolute values, dilation, and adding the angles, rotation. A polar form of a complex number is convenient to find roots from complex numbers. Consider a non-zero complex number w in its form w equals absolute value w times cosine phi plus I sine phi. If z equals absolute value z times cosine theta plus I sine theta is such that z to the power n equals w, then absolute value z to the power n equals absolute value w, and cosine n theta equals cosine phi, sine n theta equals sine phi. It follows that the difference n theta minus phi is a multiple of 2 pi. Then the different possible values of theta are theta equals phi over n plus 2 pi k over n, k greater than or equal to 0, less than or equal to n minus 1. We get exactly n different roots of order n from w. In the upcoming figure, we can see the 3 cubic roots of the complex number I equals cosine pi over 2 plus I sine pi over 2. Cubic roots of I. If z equals absolute value z times cosine phi plus I sine phi, z cubed equals I, then absolute value z equals 1, phi element of pi over 6 plus 2 pi k over 3, k equals 0, 1, 2, equals pi over 6, 5 pi over 6, 3 pi over 2. Thanks for watching.